between the return that we saw and the value function. Whereas TD0 actually converges to the solution of the MDP that best explains the data. So implicitly what TD is doing is it first fits an MDP, and then it solves for that MDP. So whatever data you've seen so far, it will find the solution to the maximum likelihood MDP model that explains that data. So this is just math to say exactly that same idea. It's just saying that, first of all, let's find the MDP that best fits the data, and you can do that just by counting transitions. So here this is just saying let's make the transition dynamics count all the transitions we've seen from state S and state A to some other state. Let's count those transitions and make that the probability. Just count the transitions and divide by the total number of times we're in S and A. And the reward is just the mean reward from state S and A divided by the number of times we were there. It's just fancy notation. This bold one means an indicator function, saying each time this event occurred, this indicator has value of 1, otherwise it has value of 0. Yeah?
If you know the MDP, can you give it to Monte Carlo so that it doesn't, do you know what I mean? So
right, so the question is, if you know the MDP, can you give it to Monte Carlo to ask it to sample from the MDP and work from those observed returns? We'll come back to that in lecture 8 or 9. We'll do exactly that. It's a good idea. Okay, so let's come back. We were trying to understand the advantages and disadvantages of Monte Carlo and TD. And so I really just want to summarize the third type of advantage now I think we can understand better, which is that a Markov decision process has the Markov property. And TD exploits this Markov property, exploits it by building implicitly this MDP structure and solving for that MDP structure. And that means that in Markov environments, TD normally is more efficient because it actually makes use of that Markov property. It makes use of the property that you don't need to just blindly look at complete trajectories. You can understand the environment in terms of states, and we know that certain properties of those states have to hold, that the state has to summarize everything which came before. And that's why TD is more efficient. It's another way to understand it. Whereas Monte Carlo does not exploit the Markov property. It ignores the Markov property. But one benefit then is if you're in a non-Markov environment, partially observed, you can't just rely on the state signal, you get everything's aliased and messy, then Monte Carlo can be a better choice. And often we have some spectrum between these where you're maybe a little bit non-Markov, and then the question is, how far between these should you go? Okay. Right. So just to sort of summarize where we're up to, this is just a few slides to give a sort of pictorial summary of what's going on. Yeah, question?
You said sometimes we're a little bit non-Markov. Does that mean an MDP even still applies?
Okay, let me explain that comment. So I said you can be in a situation where you're a little bit non-Markov. So the question is, does an MDP still apply? So under the hood, there can always be an MDP which defines the way that the environment works. And the question is, what do you observe as an agent? So a partially observed Markov decision process is where you get to observe some function of the state. You get to see some part of the state. You get to see like certain cards but not other cards, or you get to see certain statistics but not other statistics. So there's an MDP running under the hood. You get to see some part of it, and now the question is, how do you deal with that? So there is an MDP, yes, but if you just try to use your observed statistics as your state representation, TD wouldn't work very well. TD0 wouldn't work very well. Monte Carlo would still do the right thing given that representation you've given it. So it would still find the expected return conditioned on the information that you've shown it, which still might not be great, because if you have a blind robot walking around, its estimates of the value aren't going to be very good compared to if you let it see everything. But you still want to make sure that it can consistently estimate values, even if it is blind, even if you only give it partial information. Okay. So let's just try and pull things together a little bit. So we've seen that we have these different updates which take these particular forms, and we can think of these as like backups. That we started in some state. Imagine we're doing something like our backup diagrams we saw for dynamic programming now, where what we're going to look at is you start in some state, and implicitly there's some kind of look-ahead tree. Like, we're in the MDP, and in this MDP, from this state, there are two actions I could take. I could go take this action or this action, and from those actions, the wind might blow me here or it might blow me here. Then there's some actions I could take. This one might terminate. This one the environment might take me to here, and so forth. And the question is, how do we make use of this look-ahead tree to figure out the value function at this root node here? And so what Monte Carlo does is it basically samples one complete trajectory along here. It samples it samples an action from the agent, it samples where the wind might take you, it samples an action, samples where the wind might take you, samples one consistent trajectory. Just by running that and interacting with the environment, you get one sample of this whole thing. And then you use that sample to update the value function at this root value here. And we also do it at every intermediate value. This is just showing what happens for one. We're focusing on one state here, but we also do all these other updates when we run. Temporal difference learning, the backup is just over one step. Where we sample the environment, we sample our own action, we sample the environment, we look at the value function where we ended up here, and now we back up that value function here towards the value function at this root node here. So we don't go all the way to the end like we did in Monte Carlo, we just look one step ahead, we get a sample of what happens over that one step, and we back up that sample towards the value function here. Now let's contrast that to what we did in dynamic programming. So in dynamic programming, we also did a one-step look ahead, but we didn't sample. We had to know the dynamics, and we used those dynamics to basically compute a full expectation. Well, now we consider this action here, we took a full expectation where we had to know the probability the environment would take us here, we had to know the probability the environment would take us here, and then we could sum these values together, weighted by their probabilities, take a max over our actions, and do a complete backup to figure out the value here. So if you know the dynamics, you can do this full look ahead, and that backs you up completely to give you this value here. And just to complete the space of possibilities, you could also do an exhaustive look ahead of this entire tree. You could do something which is like dynamic programming, but you went all the way to the end and did a complete backup, and that's an exhaustive tree search. So you get an exponential blow up in the size of the update that you do for just one state. So let's try and tease these apart into dimensions that we can understand that sort of define our algorithm space. So the first dimension is whether or not we bootstrap. So Monte Carlo does not bootstrap. So bootstrapping, again, remember, is this idea that you don't actually use the sample, you don't actually use the real returns, you use your own estimate of the returns, you use your own value function as a target, and use your estimated value function to kind of give you an iterative update, rather than using real returns or real rewards. So Monte Carlo does not bootstrap, it uses the real returns all the way. But TD and dynamic programming both bootstrap. So in both TD and dynamic programming, we're doing something like the Bellman equation, where we look at the immediate reward you get, plus the value function at the next step, and we bootstrapped from our estimated value at the next step. So in both of those cases, have that situation, you've got your robot, you take one step of real experience, but then you make a guess of how much value you're going to get from here until the wall, and use that guess of your value to back you back up, either from one sample in TD or by doing an exhaustive full width backup in dynamic programming. The other dimension is whether we sample or take full width backups. So Monte Carlo samples, so it samples the environment. We don't need to do a full width exhaustive search over all the things the environment might do. We sample the MDP dynamics. We sample our own policy. Whereas dynamic programming does full width updates. It considers every possibility exhaustively and backs them up exhaustively. TD samples as well. Okay, are these two dimensions clear? Good. So that gives us this picture, sort of gives us the space of unified view, if you like, of methods for policy evaluation. We'll also have the same picture for control that applies throughout reinforcement learning, where you can either use these full width backups that do this exhaustive look ahead over all the different choices you might make, or we could sample the dynamics. And then in this dimension here, we've basically got methods which bootstrap from our value function after one step. So they only have to go like this shallow look ahead. They look ahead one step and then update from the value function here towards the value function here. Or in dynamic programming, we do a full width look ahead, but we update from the value function here to the value function here. In contrast, we can do these deep backups with Monte Carlo, where we go all the way to the end of the episode and we look at what happened right at the end, and we back up the actual return all the way to the value function here. Similarly, with exhaustive search, you can do an exhaustive look ahead all the way to the end, back that up all the way to the root, without ever bootstrapping from your own value estimate. Okay, and now the final piece, in the remaining 20 minutes or so, I'd like to talk about a spectrum of methods in between these shallow and deep backups. So it's not actually the case that you have to do either or. You don't have to do either TD learning or Monte Carlo learning, because it turns out that there's a unifying algorithm which has either end as its special case. And that algorithm is called TD lambda. We'll see that lambda basically lets you pick your place along here, where you can be either shallower or deeper according to a value of lambda. Yeah, question?
So I have one question about the TD learning algorithm. So whenever we sample state action transition to another state, we always update the value function for the first state into this action. So it's sort of saying I'm updating my estimate of the state where I was given the current action, and I assume that actually the next value is correct. Why can't, if we do the opposite way, so we update the value function for the forward state,
Okay.
we basically do the opposite.
All right. So
In that kind of scheme, wouldn't it be true that it should also work?
yeah. So it's a great question, which is why do we assume that the value after one step is more accurate than the value before one step? Why not? Why not reverse the dynamics and do it the other way? And the second part of the question was, would the alternative algorithm give the right answer? So the answer is that it will give the wrong answer. In fact, even if you do something like just make these things close to each other and try to minimize the mean squared error of your TD error or something, you find the wrong answer in stochastic MDPs. That's a well-known fact. You actually get the wrong answer by doing it the other way. So why? So let's get the intuition. So the intuition is that if you take one step, you're always, in a sense, a little bit more accurate because you've seen one step of reality in between. So you've seen one step of reality. That step of reality involved one step of the real reward and also one step of the real dynamics. And then you estimate your value function where you ended up. Okay? But because you've included one step of the real dynamics and the real reward, you are, in some sense, more accurate. You're more accurate than where you were before. And if you take enough of these steps, you end up grounding yourself completely in the real dynamics and the real reward of what happened. So it's because you're involving one step of the real world. Whereas if you go backwards, it's like you're starting from a situation where you've already taken that step, you're closer to your goal, you've already seen this real step of what happened, and now you want to use this guy to, you're going to move this guy towards your estimate of what happened before you saw that real step of the environment. There's no reason to think that that estimate is actually going to be better, and often it's going to be worse. So I think the key is, and this actually comes apparent in the math if you actually look at the reasons these algorithms converge, like contraction mappings and so forth, it's because you take one step of real dynamics, and that real dynamics always brings you closer to the ground truth.
Yeah, but if you make the step backwards, you still observe the real dynamics of the reward that you get. Shouldn't that get you closer? And I'm not
No,
sure
I don't think you do in
also
reverse.
For given MDP, does there exist another MDP which can produce the observations in reverse order? I would guess not, if this one doesn't convert.
So if I have time in future lectures, what I'll try to do is give a specific MDP for which your proposal fails. And it's very simple. There's a very simple MDP, and we can maybe do it afterwards. Okay, but I really want to do TD lambda before we run out of time. But yeah, great question. Okay, so far we've seen this idea of temporal difference learning, where we said, okay, you can take one step of reality and then look at the value function after one step. But why not take two steps of reality, where you take two steps and then you look at the value function where you ended up and use that value function after two steps to back up towards your value function of where you were 2 steps previous, or 3 steps, or n steps. All of these are valid ideas. They're all reasonable. And so what we're going to do is generalize the idea of TD learning to these n-step predictions. So TD we can think of as this special case. TD0, what we've seen so far, is a special case where we take one action, so we see one step of the environment, we end up in some successor state, and we update the value function of that successor state towards our value function at our original state. But we could just as well do the 2-step version, where we take one step to our next state, another step to our state 2 time steps from now. We update the value function, our reward plus our value function, gives us our estimated return, and we update our value here towards that estimated return. So you can do that for any number of steps. You can always say, well, I'm just going to observe some number of steps of the real world, see how much reward I got along those steps, add on my estimated value from that point onwards, and that quantity is a valid estimate of the overall value function. And we can use that estimate to update our original value function in the correct direction, based on the comments of the last question. Okay, so let's specifically try and just write out what that means. So far we looked at the TD0 estimator. That's when n equals 1. So when n equals 1, we make what we call a one-step return. This G1 is a one-step return. Where we just look at one step of the real return, and we look at our value function in the state that we ended up in after one step. But now let's define the two-step return. So the two-step return, this G2, is the reward after one step, plus the discounted reward after two steps, plus the twice discounted estimated return from that point onwards. So this is our value function. Our value function tells us, from that point onwards, how much reward are we going to get? And then we can just say our overall return, our estimate of the overall return is our real reward after two steps, plus our estimate of what's going to happen from that point onwards. So we can do this for any n, and in the case where n goes to infinity, we end up with the Monte Carlo estimator, the real return. So we start off with TD0 here, and we get all the way to Monte Carlo here. The reason we get to Monte Carlo is because G infinity, we use all the steps of the real environment. We look at our real reward plus our discounted real reward at the next step, all the way until the end of the episode. We're just looking at the real rewards of what actually happened in that trajectory, and that's exactly what Monte Carlo does. It looks at these real quantities and it uses those as our targets. And so now we can define, if we just generalize this for any n, so the n-step return just tells us we're going to take n steps of real reward by really interacting with the environment. So these are just random quantities that depend on our particular trajectory of where we ended up over n steps. And then after n steps, we can use our estimated value, our current value function, in the state that we end up in after n steps, as like a proxy for all of the rewards that we haven't observed from that point onwards. And we can use that as our estimator. And we can plug this in the same way that previously we took our Monte Carlo estimate and we plugged in our TD0, our TD target, in place of the actual return. Now we're going to plug in our n-step return as our target. So what's this telling us now? Again, we've got like this error term here, where we're saying we started off with some estimate of the value function. We ended up, after this particular trajectory, with some n-step estimate of that value, where we saw some number of rewards and plus our estimated value. So this is our n-step estimate of the reward. This is what we thought the reward was going to be. That generates an error signal, and we just update our value function a little bit in the direction of that error signal to correct for that error. So this is valid for any n. So which n is the best? That's the natural question. Should we be using n equals 0, which was TD0? Should we be using n equals infinity? Should we be using n equals 17? What's the right thing to do? So this is a little study just on the same random walk we saw before, but now this is a larger case. I think it's got 21 states or something like that. And it's just a little study to look at how the performance, in terms of this root mean squared error that we looked at before, how it varies across different step sizes that we varied before, but also across different choices of n. So these little numbers in here tell us the choice of n when we do n-step TD updates. And the top and the bottom diagrams are very similar. It's just about whether we do online or offline updates, and that means whether we immediately update our value function or whether we defer the updates of our value function until the end of the episode. And you get slightly different results, but the character is still the same, which is to say that as n approaches infinity, up here somewhere, you see what would happen if you're using Monte Carlo learning. So you get very high errors. I think this is these are short runs. With this, the total training time is short, which is why Monte Carlo, the difference between them is so exaggerated here. But we see that Monte Carlo, the variance of Monte Carlo is high, and it doesn't do very well. TD exploits the Markov property, it's lower variance. It does better. So this is TD0, but in between you get this sweet spot where if you look ahead just sort of the right number of steps in your trajectories, you can propagate information backwards more efficiently. You can kind of each TD update is not just propagating information back over one step, it can propagate information over multiple steps, over n steps at a time. So you can kind of move information more quickly across a long chain now by using n greater than 1. And so we see there's some kind of sweet spot with n around 3 or 5, but it's sort of unsatisfactory in that you can see that even between the online and the offline, the best n changes, and if you change the size of your random walk, the optimal n changes again. Like if you were to do a 100 state random walk, you would see that all of these values would be shifted over so that you should to favor larger n. And so it's a little bit unsatisfactory. We want to have algorithms which are sort of robust across many different ways to many different n's. And so what we're going to do is try and come up with an algorithm which gets the best of all n. That's the goal, to efficiently consider all n at once. So how do we do that? Well, the way to do that is to notice that we can average over these n-step returns. We don't have to just commit to one of them. We can actually take a target which combines multiple n-step returns together. So for example, consider this case where we're just going to do one backup towards the average of both of these. So basically what we're going to say is our estimate of the return now is going to be what happened after 2 steps and the value function. So we're going to take 2 steps of real reward and the value function after 2 steps. We're going to average that with 4 steps of real reward and the value function after 4 steps. We can average those things together, call that the target, and that thing is going to be more robust because it kind of gets the best of both of these cases. And we can use that as the target for our TD learning. And so the question is, how can we efficiently combine all n in this way? Can we come up with a scheme that, without increasing the algorithmic complexity, lets us deal with all n? And the answer is, yes, we can do that efficiently. And the algorithm basically is called TD lambda that does that. So the main idea is to use this quantity which is called the lambda return. And the lambda return is like a geometrically weighted average of all n going into the future. And so the idea is that we've just got this constant lambda, which is between 0 and 1. And this constant lambda tells us how much we're going to decay the amount that the weighting that we have for each successive n. So we're basically going to have a weighting of 1 minus lambda for this one-step look ahead, and then we're going to keep multiplying successively by lambda. So this 1 minus lambda is just like a normalizing factor that makes all of our weights sum to 1. So what we're going to do is multiply our weight by lambda when we go to from n equals 2 to n equals 3, by lambda again when we go to n equals 4, and so forth. So each one is successively weighted less and less and less, until we get to the end of the episode, and we basically give all the remaining weight. If we were to continue this diagram all the way to infinity, we're going to sum the weights of all the remaining ones, gather those weights together, and put them into this final update for the last one. Okay? So this is what it looks like. So we use a weight. For every n-step return, we weight that n-step return according to 1 minus lambda, this normalizing factor, and then just lambda to the n minus 1. And so this is our lambda return. This G superscript lambda tells us our weighted sum of all of our different n-step returns. So we're going to weight these together geometrically. And now again, we're going to do the same trick, which is we're just going to use this G lambda as our target now for TD learning. We're basically going to move, we're going to have our estimate V. We're going to use this thing as the target, our weighted sum of all of these n-step returns. And we're going to generate an error. This is what we thought the value was going to be. This is after our trajectory, after a whole episode, we can weight all of our n-step returns, come up with this very robust estimate of what the return actually ended up looking like, and we update our value function a little bit in the direction of that error signal. Is that clear? Maybe. Yeah, question.
Is it always the case that the last weight in this formula is smaller in comparison to the previous?
It's always the case until the final step, until the algorithm terminates, that the weights are getting less by a factor of lambda. The final weight actually can be larger. Just think of this as you can always take any episode that terminates and replace your terminating MDP by an MDP that goes on forever, and it just stays in the same state, getting 0 rewards again and again and again. And so all this is doing is instead of, so you could, you could have a diagram which goes on forever, where these were getting longer and longer and longer, and the value function wouldn't be changing each time because you'd just be stuck in that same terminal state. And then all this is doing is gathering together all of those final ones into one update because we know that the episode's terminated. So it's just an efficiency that we gain by knowing that the terminal signal has this special effect that nothing else is ever going to change the value after that point. But it can be larger. Okay, so it looks something like this, where we've got this weighting, and this weighting decays geometrically like this over the number of steps that we look into the future, and we generate this lambda return, and we kind of sum up all of the final steps into one bigger weight that we use to deal with the final return, the last step of the episode. You have a question?
Why is it geometric why don't we use some other convergence?
Okay, great question. So the question is, why use geometric weighting? Why not some other weighting? The answer is that it makes for an efficiently computable algorithm. So the geometric weightings are memoryless, and that means that you can actually do this in a very efficient way that doesn't require either storing or computing something different for each of your n-step returns. So you can do TD lambda for the same cost as TD zero, basically, same computational cost. And that's only true for geometric weightings. You can, I should say that it is possible to come up with geometric weightings where the lambda varies per time step, and that gives you a much broader class, and that still has the nice property. You can vary the lambda that you multiply by at every step of the algorithm. That gives you a much broader class, but it still satisfies this nice property. So we are going to make use of that property shortly as well. Okay, so what we've seen so far is that we have what we call this forward view algorithm, where it was a bit like Monte Carlo, that to do this we had to wait all the way until the end of the episode to get our n-step returns. But you can only compute what happened after 10 steps from now. Once your whole episode is finished, you can go back and look at all your n-step returns, average them together, get your lambda return, plug that into your algorithm. So this suffers from some of the same disadvantages that we had with Monte Carlo. So that's the forward view of TD lambda. But what's nice about TD lambda is there is an equivalent mechanistic view that achieves the same results as forward view TD lambda, but without having to look into the future, without having to wait until the end of the episode and gathering those lambda returns. So this is just to say, this is the same diagram we had before, showing on the large random walk. Now, how sensitive is this to lambda value? And it's actually, we see that there's a sweet spot again in lambda, but it's actually much more robust, that this value of lambda would be the same, that works best regardless of the size of the random walk. It's much more robust to the change in the environment, and it does well, as well as the best n, just by averaging over these things. And lambda equals 1 is Monte Carlo, lambda equals 0 is TD0. And we see that we can do much better. And you often see these kind of curves where there's a sweet spot in the lambda curve between 0 and 1, where you get just the right trade-off between bootstrapping and the bias variance trade-off. Okay, so now let's come up with a backward view. How can we actually achieve this, but with the nice properties of TD learning, where we update online every step from incomplete sequences? And that is the TD lambda algorithm. So to understand that, I'm just going to put up one diagram here. Okay, so imagine you thought you're a rat again, like in the first lecture, and you thought you were going to get this nice piece of cheese, but then you hear a bell 3 times, a light comes on, and you get electrocuted. Okay, so who thinks that you got electrocuted because of the bell, and who thinks you got electrocuted because of the light? Let's just have a show of hands. Bell. Light. Okay, so most people thought the light. Okay, they're both reasonable answers. If you thought that the most frequently occurring state caused this event, then you would assign credit to your error to the bell. You would say the bell happened more, so that was probably the, I thought that I should change my thinking more because of the bell than I should because of the light. But there's also a recency heuristic, which apparently you guys are partial to, which is to say the most recent thing which happens should basically be assigned credit for the error that we see. And the idea of eligibility traces is to combine both these heuristics together. So what we do with eligibility traces is we look over time at the states that we visit. And the more So this is the eligibility trace for one particular state. And this is the moment at which we visit that state. And what we do is we basically, every time we visit that state, we increase the eligibility trace. And as we start to not visit it, we decrease the eligibility trace exponentially. So we increase it, we see it, we increase it again, we increase it again, and we don't see it for a long time, and it sort of decays off. And so this gives us our frequency and recency heuristics combined together. And what we do is we basically update, when we see an error, we update the value function now in proportion to the eligibility trace, in proportion to how much credit we think was assigned to being in that state. Like how much was being in this state of hearing a bell the cause of this error that I saw, and we update the value function there directly in proportion to the eligibility trace. So this gives us the backward view TD lambda algorithm. And so what this gives us is this following algorithm, where for every state we're going to keep one of these eligibility traces. That's trivial computationally, it's just a simple operation per state. We update the value function for every state in proportion to both the TD error and the eligibility trace. So we compute our TD error. This is what we thought the value function was going to be. This is our estimate of the value function after just one step. So this is the one-step TD error. And now we basically update our value function in the direction of the TD error in according to our credit assignment. So we basically see this error, and the things which have the most eligibility, which we think are most responsible for that error, get updated the most. And so this has this like backwards view now, where we're no longer looking into the future. It's more like this TD error is being broadcast back to every state in the past, and the value function at each of those states is updated in proportion to the TD error. So how does this relate to the algorithms we've seen so far? Well, trivially, we can see so far that when lambda is 0, that this reduces to the TD0 algorithm. So if we plug in the eligibility trace for lambda equals 0, we see that the eligibility trace will be, when lambda is 0, basically what that means, so lambda is telling us how rapidly we decay this thing. If lambda is 0, we declare it completely, straight down after we've seen a state. So that basically means we only assign eligibility at the state where at the moment that state is visited. And so we basically update our value function in proportion to this thing, which only will be updated if we actually visit that state. And that's exactly what TD0 does. It basically gives us our update. But for the state that we visited, we update the value function in proportion to the TD error for that state, only if that state was visited and never otherwise. Okay? At the other extreme, we have lambda equals 1, and in that case, the credit is deferred all the way to the end of the episode. And so if we're actually in an episodic environment, this has the nice result that actually if you were to accumulate all of the updates that you do using this backward view, you actually end up getting the same set of updates. The sum of those updates is the same as for the forward view of TD lambda. So the backward view and the forward view of TD lambda are actually exactly equivalent when you do offline updates. They're the same algorithm. So it's just a mechanistic view that can be implemented efficiently. You only have to look backwards, you don't have to look forwards in time. And that's the TD lambda algorithm, which helps you achieve this principled view which we understood in terms of this forward view, where we were doing these averaging over these n-step returns. So this theorem shows that they're equivalent. There's some notes which you can look at offline that prove the equivalence and give a bit of intuition into it. And finally, there's just a mention of some recent work that shows that actually this result has been extended even to online updating as well. So even if you change your value function as you go along, you can also achieve the same equivalence using a recent method from last year. So that's it really. So that's all in the slides. So just before we close, any last questions about that? So TD lambda basically gives you a spectrum. It gives you a spectrum between TD0 and Monte Carlo. And it has two implementations, this forward view that gives you this theoretical way of averaging over all your n-step returns, and this backward view where you accumulate these eligibility traces